In this video I am going to summarize or preview, depending on how you're attacking this. We're going to look at the analysis of the Rust variable for our car trade-in value data. So I'm going to start out, and I have fit the simple regression model with the dependent variable of trade-in value and the single independent variable Rust. Remember, Rust is a binary or 0-1 variable. It only has the values Rust equals 0, meaning the car does not have a significant amount of rust, or Rust equals 1, meaning the car does have rust. So here is the output for that simple regression model, and what we see is, first of all, we have a fitted model. Trade-in value equals 8560 minus 1600 times rust. We also notice that the rust variable has a p-value of 0.1169, meaning this model is not demonstrating a significant relationship between the rust variable and the trade-in value. We might say that rust does not appear to have a statistically significant effect on trade-in value. Now, as always, we have to remember that does not prove rust has no effect. It simply proves that with this data we are failing to show that rust has an effect. Nonetheless, it will be somewhat interesting to look further at the results of this. If we compute the y-hat values at the two values of the independent variable, when rust equals 0, then our predicted value is simply the intercept of 8560. And when rust equals 1, the predicted value is the 8560 minus the 1600. And we could interpret, if it were statistically significant, we could interpret this negative 1600 as the decrease in trade-in value when the car has rust compared to when the car does not have rust. However, as I noted before, we are not seeing a statistically significant relationship. The p-value is too large. We can probably see why that's happening if we look at this scatter plot of the data. Here's our red line, y equals 8560 minus 1600 times rust, so it's dropping by 1600 from the 8560 when rust equals 0 to the 6960 when rust equals 1. And relative to the magnitude of that change, look how much random variation we have above and below the line. So we can't really say we certainly have a down-sloping line. We always come back to the question, could a different random sample from the same population have just as easily maybe given us a slightly upward sloping line? So when rust is the only independent variable, we are not seeing a statistically significant effect. Nonetheless, if we look at the multiple regression model, where we have a variable for sticker price and mileage and rust, notice now we are seeing a small p-value for the rust variable, or now we are able to say that it appears that rust does have a statistically significant effect. We should probably back up and first note that the overall model has an F ratio with p-value less than 0.0001. So overall our model is showing that something is being explained, and the p-values on the sticker price and mileage and rust are all less than 0.05. So all three variables are showing up as significant. Now, why is the rust variable showing up as significant in this multiple regression model when it did not show up as significant in the simple regression model? Well, the simple explanation is that this model, the simple model, failed to control for example, variation in the mileage in the car and the sticker price. Some of this random variation above and below our fitted line, some of this is because the cars had high sticker prices, and they would probably be the ones above the line. Some of them have low sticker prices. Some of these have low mileage. Those again are probably the ones or contribute to why they might be above the line. Some have high mileage, which is why they might be below the line. So in other words, the effect of sticker price and the effect of mileage are showing up as part of the error term, the unexplained random variation, when rust is the only independent variable. In this larger model, I've taken the effect of sticker price and mileage out of the error term. They are no longer contributing to the unexplained portion of the variation, and they are now being explained. because I have a variable for sticker price and a variable for mileage. And this has allowed us to see that yes, there is an effect of rust. So in one particular context, we might be looking at this data primarily to see what the effect of rust might be. Notice if I simply look at the effect of rust by itself, I don't have enough data to show the effect of rust if there is one. But if I add sticker price and mileage, I say I'm controlling for those variables, and now I can see that rust does have an effect. And the effect of rust currently is estimated to be about a negative 1310, negative $1,311. Now, we'll notice that's quite a wide confidence interval around that. Nonetheless, this is our current point estimate. You should also go back and note that compared to the variable that only had sticker price and mileage, it appears that adding rust to the model has increased the adjusted R-square. So we've increased the adjusted R-square, our new variable has a small p-value, so adding rust to our model is giving us better predictions of the car trade-in value.